Let's talk about the Steam Machine. My name is Timothy Lattice, and this is the NeoKino Graphics channel. So as a developer, I'm excited about this box. However, tech press has been quite negative in some respects. It's almost as if perf per dollar is the only thing that matters these days. I'd ask, do all my vintage consoles somehow become worse in quality each time a faster lockdown OEM box shows up in the market? Let's talk about pricing. Historically, Valve has had fantastic pricing on Steam Deck. I would expect Steam Machine to be competitive on pricing too, and competitive on pricing relative to the market condition. So for instance, if we're still dealing with this RAM cost problem, yeah, its costs are going to be higher, but also all the other hardware coming out is going to have the same problem. I think it's also important to normalize pricing in the context of not having a subscription. So for instance, if I go and buy a 2025 PlayStation Plus pricing for just the essentials, and I do that, say, for 4 years, that's $320. And for instance, if I'm doing something on a 10-year life cycle, that's $800. There's a lot of other value for the Steam Machine that I think is very important. To me personally, the fact that it's not running Windows is worth a lot of money. And the fact that I don't have to manually take Windows off and install Linux, that's going to save me a tremendous amount of time. It supports emulators, supports modified games, has a desktop, which is absolutely essential to doing development, and it's free and open. The way I see it is supporting the Steam Machine is kind of like a big anti-enshittification step. It's a way to step back towards what we had before in the old-fashioned Windows. The NVIDIA Envy players are most likely going to market AI scaling TAAs and ray tracing performance as your features for the future. And likely, they're probably even going to compare AI scaling TAAs to justify potentially lower than expected performance when scaling is not there. And we've seen this already, we'll say, with NVIDIA GPUs. So the comparison, perhaps in the future, might be, well, we get the new hardware with AI scaling to the old hardware without AI scaling. This isn't really apples to apples. We'll see later in this talk, there's really no need for AI to do scaling TAA. Let's talk about the first one, better RT. I'm not really excited here. Optimized titles will be minimizing RT usage. Non-RT workloads are going to dominate runtime. If we take the example presentation of the latest id Tech, you'll notice there's a giant change in world sampling between PS5 and PS5 Pro. However, world sampling is a small percentage of the whole total frame time. So if you optimize this 0.045 milliseconds to 0.038 milliseconds, it's not going to do much to frame time. However, let's say in the future we could optimize this to 0 milliseconds a frame. Certainly impossible. However, it's not going to change the game. It's still going to be a 60 Hz title, even if the ray tracing hardware was totally free. So let's move on and talk about ML scaling TAAs. I'm extremely not excited about this one. We already know that the leaked FSR 4 works down to RDNA 3, so it will potentially port to the Steam Machine, maybe the leaked copy or maybe some official copy in the future. However, TechSpot did some interesting performance comparisons, and they normalized performance, and what they were seeing is roughly 2.3x area scaling for XeSS and FSR 3.1, and then that would normalize against 4x area scaling for FSR 4. This is going to be the one with FP8, and then 9x area scaling for FSR 4 with the fallback, the int8 version. That's a substantial amount of scaling. That's not the direction we really want to go. If we were to compare this against STP Alpha, what's in Unity today, it's substantially faster than FSR, and it's similar to FSR 4 in quality. So it's way better to use the non-ML based stuff, especially as you're scaling down. Well, it's interesting, the tech press basically ignored STP completely. However, there was one Redditor that compared it, and I found the comparison pretty interesting. And keep in mind, this is STP at Unity with some bugs versus FSR 3. The STP was never really finished. It doesn't work well at 16x scale, but of course that's what the user decided to run. We can look at some screenshot comparisons here. This is running FSR 3 at 9x area scaling, There's a lot of artifacts in this. It's not very sharp. Then the user runs 16x area scaling in STP when STP has a bug, specifically that hurts 16x area scaling, and the quality is actually not too bad at this point. If we look at background of STP, for those who are not aware, we can look at the timeline. One way we can do it is just by looking at the GitHub. STP was made by me and also Greg. Greg did the systems integration. It was amazing working with Greg, to be honest. So around 2023 of September, we had FSR 3 that launched. Around November of 2023, STP algorithm in Unity was cut, meaning after that point, there were just bug fixes until the next major algorithm revision was done. But that never happened. In 2024 February, Unity's stock price got so low that Unity was looking to cut employees, and I didn't make the cut. That was when STP algorithm development ended. 2024 in April, there was actually a game that shipped with STP. That was Harold Halibut. I actually don't remember if they got the early or the later version of the STP algorithm. There was an alpha and there was a beta. The beta is what would be in Unity today. Unfortunately, Unity's GI had introduced ghosting before STP, so it couldn't be artifact free. Now, even with that artifacting from the Unity GI system, it still was way better than DLSS in that game at the time. And never got any tech press talking about it, which was interesting. And then 2025 in January, you got DLSS 4 that launched. This is long after I'd stopped working on scaling TAs completely. So I had some time to think about this over the past year. I had a lot of ideas taking up space in my mind since STP, a lot of things I wanted to finish. I think there was a huge opportunity that Unity lost by not pursuing and marketing STP and finishing it. And now I have better ideas since STP, things that deserve to be out there. So my current goal is to put everything I've thought of after getting fired from Unity into a new algorithm. And I'm going to call that algorithm AFP for AI Free Post. This is in development now. It's in my weekends and my evenings, basically. I plan to release it as public domain after it ships in a game. I'm hoping to restore the balance to the universe. That way devs can easily scale down to Steam Deck, and there's no need for AI hardware or black boxes moving forward. Shifting gears, let's go back to talking about the Steam Machine. The Fox does an amazing job of actually building one of these things based on the estimated specs and already doing a review of performance. So if you want to get a good idea of its estimated general game performance, I would say just watch this YouTube channel. So let's actually dive into specs, and we'll talk about docked mode for the handhelds in this list. And this is going to be a lot of numbers and a lot of systems, but basically we're looking at, if we look at from the Steam hardware side, we have the Steam Deck at 1.6 teraflops and 88 gigabytes per second, and the Steam Machine probably around 17.6 teraflops and 288 gigabytes per second. Now, if we're looking at this number, you'll notice that some of these teraflop per second numbers are underlined. And this is the era of dual FP32 FMA. I call it cheating, because they didn't increase the actual instruction count. What they did was they dual issue certain instructions, such as the FP32, and therefore it massively inflates the teraflop, but you can't necessarily always get dual issue of every instruction. So realized performance, you'll notice between the deck and the Steam Machine was, say, around 6, but the actual teraflop difference, if you look at paper specs, is substantially higher than that. So it's something we have to keep in mind when we're looking at, say, RDNA 2 and prior machines compared to RDNA 3 and later machines. Probably at the bottom is going to be the Switch 2, but I would say that the Switch and the Steam Deck pretty much hit the bottom of the what the AAA space is going to have to deal with for a substantially long amount of time. The last console, which would probably be the low end, would be the PS4 these days at 1.8 teraflops per second. Then we have the PS4 Pro, which is somewhere in the middle ground between the deck and the Switch 2 and the Steam Machine and the PS5. And then if we look at the high end for the console space, and I'm just talking about the PlayStation stuff here, not the Xbox, but PS5 Pro at 33 teraflops, course, this is inflated teraflops due to the dual issue again. Now, Moore's Law is dead. They have some estimates of possible future consoles. And if we look at his estimates, his handheld estimates are around 6.8 teraflops of the cheating kind, with what seems to be maybe 205 gigabytes per second if you were to take his estimates of bus width and transactions and expand that out. That number would be similar, say, to a PS4 Pro, but not a PS5. And then he has his guess for a home console, which would be around, say, on the upper end of 40 teraflops per second and 640 gigabytes per second. So now we're looking at something that's a little bit faster, say, on paper than a PS5 Pro. Now, if we round this out with actual shipping GPUs on PC at the high end from both vendors, we have a 9070 XT, close to 50 teraflops of cheating teraflops, and 640 gigabytes per second. And if we look at the ultra high end from NVIDIA, we're looking at something that over double that. If we take a high level view of this, the existing consoles are going to have a really long tail. And the new won't necessarily displace the old. It might take a long time for that to happen. It is likely that the old, such as the PS5 and the handhelds, will be the grounding point for AAA performance min-spec. For instance, we're going to be porting to Switch 2 and AAA portability for quite some time. And if we mix this in with the PC high-end of current days, the future estimates look a lot like the PC high-end today. In other words, not much really changes. There's another way we can look at the Steam machine, and that is to look at the video ports and to see what they're capable of. Apparently there's some issue with extending past HDMI 2.0 in Linux. I do not have any information on that. However, of the two options, DP 1.4, that one looks like the better one. Use DisplayPort. And if we look at the maximum of what you can get on 1.4 bandwidth, that's HBR3. Hopefully this one will go up to that point. You'll notice some interesting configurations here, such as if you're in SDR mode at 8 bits per channel, you can do 4K at 120 Hz with the display stream compression off, which is fantastic for this kind of device. If you want to push up to 240 Hz at 4K, you'll need that display stream compression on. And then as far as the HDR mode, if you're doing 10 bits per channel, you're going to be limited to 60 Hz at 4K if you don't have display stream compression on. However, if you put it on, you'll get all the way up to 240 Hz of 4K on this device, assuming that the device supports that HBR3 bandwidth. And there is another interesting configuration here, which I think is amazing, which is if you go down to a 1440p, you can do 240 Hz, and you can do it without compression on, so it might look fantastic. And I hinted at this before on the Shader BFI talk, but I think the real nice target here is actually 1440p at 80 Hz render with the 3-frame Shader BFI. So basically you get 240 Hz motion clarity for the cost of 80 Hz, which is going to be substantially awesome on this device. Now, if you do use an HDMI 2 connection, then you have some issues, right? Like, you're pretty much going to be capped at 4K 60 Hz unless you turn on chroma decimation. And the problem here is that there's no DSC in HDMI 2.0. So now if we go back and we actually look at our scaling range relative to the Steam machine, we're going to look at maybe 6 times the ALU and 6 times the memory at the top end, and the Steam machine somewhere in the middle, and then 1/6 the ALU effective, let's say without cheating, and maybe 1/3 the memory bandwidth at the bottom. So from my perspective, actually, the problem isn't really the hardware features, especially with the Steam machine sitting in the middle. It's actually more about games scaling well. Meaning if you were to build a game that scales well and has extremely good, frame rate right out of the box in the middle ground, you could get some very interesting scaling. For example, and this is coming up with something that is plausible within the, if you adjust for pixel rates and your game scales really well based on pixel rate. So on the top end, you might do 4K at 240 Hz. And then say in the middle, which would be like a Steam machine, you might do the configuration I like, which is 1440p, rendering at 80 Hz with the 3-frame Shader BFI. Therefore, you're going to get the 240 Hz motion clarity without actually having to render 240 Hz. And then at the bottom end, let's say this is the Steam Deck, you might be rendering at, say, 720p letterboxed and hitting 60 Hz. So yeah, reviewers that are looking at low-spec machines, they're saying 8 gigabytes, and they're saying, oh, this is a problem. And if you actually want to understand the reason why it's a problem, take the total memory bandwidth divided by the frame rate and see how much memory you could access in a given frame. Now this is of course a spec peak. Real bandwidth will be like, well, I don't know, maybe 80, maybe less, maybe 70. It depends on the efficiency of the algorithm. So it'll be a lot less than this, but you could see the problem at the spec peak. You got about 9.6 gigabytes per frame. You're never going to hit that, but still that's over your VRAM. So the VRAM problem at the low, crappy FPSs, like 30 Hertz, areas where you probably shouldn't be for a programmer anyway, yeah, it could likely be a problem. And, you need a lot of memory for, say, buffering, for your swap chain, for your temporal, and so on. So it's not like you can use all the memory in a given frame. You need more than what you can use. However, if we start looking at high frame rates or frame rates that actually are good to play in, like 60 Hertz of real frame rate with real low latency input, you're only going to be able to access, say, 4.8 gigabytes of frame at maximum, which is substantially less than the total memory on the machine, which means you're pretty much in the clear. Don't necessarily need more than 8 gigabytes. That's it for today. Cheers.